Winsberg from the University of South Florida. I met him at a conference on validation. It was absolutely fascinating a few years back. There is a handbook coming out with contributions from the people who attended. And in the refereeing process, I wound up talking to him about his book, Science in the Age of Computer Simulation, which is absolutely fascinating. I can't resist plugging it. I learned that, Syllogen is a thing.
There's a new book, too, by the way.
Oh, there's a new book, too. Okay.
That one just came out a couple months ago.
Philosophy and Climate Science.
Makes a great Christmas gift.
So Eric did his undergrad at the University of Chicago, grad at Indiana, and then had a postdoc at Northwestern before South Florida. And today he's going to tell us tuning models for skill. When is prediction better than accommodation? So thank you.
All right. Well, thank you very much for inviting me, Alan, and thanks for everybody to taking time out of your day to come listen to a philosopher. I'm sure that's not something you spend that much of your time doing. Okay, so I want to talk about sort of two things here: simulation models that need to be, I'll just stay close to this, I guess, that need to be tuned, and then I want to talk about this question of, which seemed to resonate with people that I talked to this morning in various ways. When is it better to be able to predict novel data than just to be able to accommodate data that you already have? I think we all have the intuition that that's a better thing, but why and when and exactly how, and how does it relate to tuning and model skill? Okay, so what do I mean? What happened here? I thought I moved you. Okay, so what do I mean by computer simulation skill? First of all, so often I take it in. This is a term that climate scientists use a lot when they talk about their simulations. They're very interested in the question of when their models have skill. And I think what they mean by skill is something a little bit different than just fit between the model and the world, or accuracy, or correctness, or truth, or anything like that. So it's a kind of purpose-dependent notion, skill, right? So it's the adequacy of a model for a particular purpose, but one where prediction plays a significant role in achieving that purpose, right? So I think skill is not the same, as I say, as fit or veracity or truth-likeness or any notion like that. And in particular, right, sometimes I think skill can be improved by reducing some aspects of fit, right? Sometimes you can make a model more skillful in some way or other, even by reducing its truth-likeness in some other respects. So that's at least one important way in which skill is different than just simple fit. Okay, I want to talk about two different kinds of examples today. Just to kind of drive my discussion. I'm going to be talking a little bit about climate modeling. That's what I've been thinking about most, as you saw from my most recent book. And I also have been talking with and collaborating with a little bit with people who do cosmological simulations, particularly ones interested in testing various dark matter models. So trying to figure out what the various models predict about galactic behavior and larger scale phenomena than galactic behavior. Okay, so, and then I take it today's main question is going to be, when is novel prediction more important than accommodation, and how is in establishing model skill, and what are some of the sort of nuances of that? Okay, so I said I'd talk about two examples. I'll just show you, so this is just show quick videos here because it's a computational center, so we should look at some videos. So this is just an output of the GFDL climate model, right? Where did the mouse go? There we go. So they're just evolving forward the atmosphere, using some combination of physics and other modeling techniques to kind of drive that behavior. They're doing experiments to try to figure out what various forcings will do to the climate system after some period of time. So you want to know things like if we add heat-trapping gases to the atmosphere, what's that going to do to the long-term behavior of the climate, both on global scales, regional scales, in the oceans, in the atmospheres, et cetera, right? So, the notion of skill is you want to know, right, is your model skillful at making those various kinds of forecasts for you? Is it skillful at telling you is global mean surface temperature going to go up by some certain amount if we add a certain amount of carbon to the atmosphere? is drought going to be more prevalent in some places, or precipitation more prevalent? So skill, right, is a very pragmatic feature that we attribute to the model. It's not exactly the same as the model being correct. And then here's the other kind of example. I keep losing the mouse. Here we go. The other kind of example is quite sort of different in a certain way, right? This is here now people simulating the clumping of dark matter from its initial condition that you kind of get from the cosmic microwave background, right? And they want to know, for different models of dark matter, let's say, what do they predict about what the observable structure of the universe will be? Do they predict that we'll see arrangements of clusters and galaxies in the way that we do? Do they predict rotation curves for galaxies of the kind that we see, et cetera, et cetera? So in both cases, right, the goal, I think, is rather pragmatic. It's different in each case, right? In the climate case, we kind of know the physics, right? Of course, we can't calculate perfectly with the physics, but we know the physics, and we want to predict, or as the IPCC calls it, we want to project what that system is going to do under a forcing that we've never experienced before, right, unfortunately. And in the cosmological case, right, it's kind of the opposite. We're uncertain about what the correct model is, right? The popular view is something like lambda cold dark matter, but there are rivals, and we want to see whether those various models reproduce known observables. But both of those depend on being able to ascertain that our simulation models have skill, namely that they're good at pragmatic tasks to which we want to put them. In the one case, a pragmatic task of making a forecast about how the climate's going to be. In the other case, the pragmatic goal of figuring out what observables we would have, what observable characteristics of the cosmos we would get under various different possible dark matter models. Okay, so these are, I take it, features that both of these models have, and many of you, I think, run computational models. I hope most of you recognize these as features that your own models have. They make substantial approximations, right? We often don't have, we would love to have good mathematical arguments that the idealizations and approximations, particularly the discretizations that we're making, are innocent. We're usually, I take it, in most of the disciplines of people I talk to, working in domains where there are not rigorous mathematical arguments, right, that our approximations are innocent. So we know often that important dynamics in many of these, certainly in both of these cases, but I think probably in many of the cases of people I talked to this morning, for example, we know that important dynamics are obscured by relatively large grid sizes that we're using in our discretizations. And so often it's also a feature of many of these models that we use what climate scientists call parameterizations, what other people sometimes I think call subgrade physics, right? So in a climate model, I can't really walk away from the mic here, sorry. In the climate model, in the climate model, right, we have pretty large grid cells, somewhere between 10 kilometers and 100 kilometers horizontally, and then maybe 20 or 30 layers deep vertically, right? And we know that lots of interesting things are going on inside that grid. Some of these are being depicted here, but in particular, cloud formation is obviously something, the physics of which is much smaller than a grid size. It's probably, in fact, millimeter or micrometer even, the physics there. So what's going on inside those grids is being parameterized, right? It's not real physics that's driving that aspect of the simulation. It's a kind of replacement physics that happens, that's happening at a different scale than the one that we're capable of resolving. And then the idea of parameterization is closely related to this other thing that I want to talk about, which is tuning. So tuning is definitely an important and sort of unfortunate feature, right, of climate modeling. So tuning, I take it, is this process of adjusting some of those parameter values kind of late in the game in order to get the behavior of the model as a whole to behave in an acceptable way. So if you're at all familiar with climate models, you might know that they all have this feature that they kind of lose energy at the top of the atmosphere. It's a kind of hard to fix feature of the basic mathematical approximation scheme, that they lose energy at the top of the atmosphere. And kind of one of the last steps of making a climate model is once you've kind of put everything together in the way you want it to be, you then compare what the model is telling you about the level of radiation at that top of the atmosphere. You compare it to the real world, and then you adjust certain key parameter values in the model in order to get that to balance more accurately than it was. Okay, so you are adjusting parameter values of these, in a way, kind of fake features of the model. Parameters, after all, we're talking about this morning. These parameters are not real physical values, right? These are kind of artifacts of the model. But even with respect to that, you know that you're now in a climate model. You're often adjusting them away from what would otherwise have been their ideal value, in order to compensate for what are hard to fix errors that are elsewhere in the code. Okay, so some climate scientists often talk about this as a balance of approximations, right? You know that the basic computational scheme you're using has this unfortunate side effect. It causes this radiation leak, very figurative expression, right? Because of this radiation leak at the top of the atmosphere, you compensate for that by adjusting those parameter values, where the parameters were in the first place kind of made up values that were there to compensate for other errors. Okay, so there's a lot of balance of approximation there, and skill then, right? Skill in a situation like that is clearly quite disconnected from verisimilitude or truth likeness or fit or anything in terms of a kind of a literal comparison of the model and the world, because here's a nice, very clear case where you are adjusting those parameter values away from, in some sense, what you might think their ideal values are, right? So if I asked somebody who was expert on clouds, in this parameterization of cloud formation in that grid box, is this value of the parameter about right? They'd say, no, it's probably much lower than that, but you've raised it higher than that in order to balance out some other features. And by balance out, what we mean is, right, get output that meets my pragmatic goals, where my pragmatic goals might be something like making these forecasts about what global mean surface temperature is going to be like at the end of the century if we don't get our act together. Okay, so it's a last step, and it's kind of done to increase the model's skill in some sense. I don't know why I keep clicking on this. That doesn't do anything. Okay. So here's I'm just going to read you now a couple of quotations about model tuning. These are all going to be from climate scientists. So this is right out of the IPCC report. This is I don't know how many of you know all this IPCC jargon, right? This is the 5th assessment report. This one came out a few years ago. Working Group 1 is the basic science group. And this is box 9.1, I think, from the summary for policymakers. So they say model tuning directly influences the evaluation of plant models, as the quantities are tuned, cannot be used in model evaluation. Quantities closely related to those tuned will provide only weak tests of model performance. Nevertheless, by focusing on those quantities not generally involved in model tuning while discounting metrics clearly related to it, it's possible to gain insight into model performance. Okay, short version, right? If you've used the data set to tune your model, you can't use that data set to test your model. Pretty obvious basic claim, you might think, right? Good. Here is, this is one of the most revealing there aren't very many good papers about model tuning, because it's, of course, not a feature of climate models that climate science are especially proud of. But there's a nice little paper from 2012 by Moritz and others. And they talk about this too. They say, including quantities in model evaluation that were targeted by tuning is of little value. Evaluating models based on their ability to represent the top of the atmosphere radiation balance usually reflects how close the models were tuned to that particular target rather than any of their intrinsic qualities, right? So if you've tuned the model to get the top of the atmosphere balance right, don't herald top of the atmosphere radiation balance accuracy as a sign that you've got a great model. pretty obvious. I think I'm going to skip to this. So this was, these were a couple of philosophical philosophers writing on climate science, colleagues of mine, and they said something that a lot of people found counterintuitive. They used the word calibration instead of tuning. It's the same thing they're talking about there. Right? Calibration is simply the common practice of testing hypotheses against evidence. Double counting, right, that kind of using the same data to test as you use to calibrate is perfectly proper. And in particular, say, right, by Bayesian standards, and I'll say a little bit about that in a bit, double counting simply amounts to using evidence in the regular and proper way. So they were taking this, what you might think is rather counterintuitive point of view. Gavin Schmidt, who, if you follow climate science stuff at all, you may have heard of, he's kind of I think the lead climate guy at NASA now, wrote a response actually in a philosophy paper, so that was kind of fun, to this. And he said, no, Steele and Vernal, that's nuts. It's incumbent on those who develop models to know that they have and have not been tuned in order to avoid inappropriate conclusions from successful tests. Right? The literature has been murky on this historically, but we need to be more honest and clear about this. We need to be perfectly honest that when we've used a data set to tune our model, we cannot herald that agreement between our model and that data set as evidence of anything. Good. Okay. So why did Verndl and Steele, what was their argument? I'm going to sort of look at their argument and see if it tells us anything interesting about what's going on in the difference between prediction and accommodation. So they're employing a kind of, you can think of this as, most of you, to the extent that you might know about Bayesianism, you might think of it as a set of statistical methods. We think of it in philosophy as a kind of model of scientific inference, because it's a kind of clear account of what goes on when you evaluate hypotheses in the light of evidence, right? And it tells you this. It tells you that the final probability of some hypothesis S is just equal to the probability of the evidence given that hypothesis multiplied by your prior probability of the hypothesis, right? So the PS on the right is the prior probability of the hypothesis. The PS on the left is the posterior probability of the hypothesis, or final probability of it. And it just follows this. This just follows from the axioms of probability theory, right? Most people are familiar with Bayes' rule. Okay. So they say, okay, but look, Bayes' rule doesn't seem to mark any difference between evidence that's collected before model evaluation and after model evaluation. Evidence is evidence. In fact, they run through the calculation. They use, here you have S1 is some model that's being evaluated with prior evidence. S2 is being evaluated with posterior evidence, and the probabilities seem to come out. They say, aha, look, Bayes' rule shows, right, that double counting is perfectly proper. Okay, what did they do wrong? What they did wrong is they forgot an important element of Bayes' rule, which is your background knowledge, right? You should always include in all the conditionals of all these probabilities your background knowledge. So you're interested in the probability of the final probability of the hypothesis, given all the other things that you knew, and given that you believed in Newton's laws, and that you believed that there's no free lunch, and that you believed all the other things that you happen to believe in your life, right? So it's important. It's often suppressed because it's kind of taken to be obvious, but it's important to remember that background knowledge is part of the conditional of all of these conditional probabilities. And once you remember that, right? So that's the little b there is our background knowledge. And once you remember that, in fact, Bayesianism kind of presents the opposite conclusion to the one that Verndl and Steele were suggesting. And it's kind of a puzzle, right, in a way. Why is that? So this was when philosophers of science were first kind of thinking about Bayesianism as a model of scientific inference in the 1980s. Clark Gleamore wrote this paper, Why I'm Not a Bayesian. And his argument that you shouldn't be a Bayesian is that Bayesianism has what he called a problem of old evidence. Okay, so those of you that are astrophysicists, I'm sure know about this, right? Newtonian gravitation got the precession of the perihelion of Mercury wrong. It was a well-known problem in the late 19th century, early 20th century. When Einstein developed the theory of general relativity, it did a much better job of predicting that precession of the perihelion of Mercury. This was considered to be a very strong consideration in favor of accepting the general theory of relativity. Right? It was second only to the Eddington starlight bending observations. But that's despite the fact that Einstein was well aware of the inaccuracies of the precession of the precession of Mercury according to Newtonian gravitation, right? And so if we go back and we look at Bayes' rule, right, anything that's old evidence, sorry, I'm going to walk away from the mic here. Anything that's old evidence is going to be part of your background knowledge. If it's old evidence, it's part of your background knowledge. And if it's part of your background knowledge, then the probability of E, given some set of knowledge that includes E, is going to be 1. So that's going to be 1, and that's going to be 1. And then your final probability of the hypothesis, given your background knowledge, is going to be equal to your initial probability, right? You can't get any boost, according to Bayes' rule, you can't get any boost in your degree of belief in the hypothesis from old evidence because it's part of your background knowledge. And this was, Gleamore said, this is why I'm not a Bayesian, right? Bayesians have this problem of old evidence. Most people thought, oh, we can give a response to that. We can give a response to that. And there are various responses. One popular one is to distinguish between knowledge that's genuinely novel, right? Literally new things that you find out after you make your model, and things that you may have known before but that you didn't use in producing your novel. So some Bayesians came up with this idea. We need to distinguish between use novel information and genuinely novel information. And then if something is use novel, we don't include it in the background knowledge. So I think this is on my slide here. Right, my revised Bayes rule says I don't actually calculate all these probabilities with the real B, which is my full set of background knowledge. I use B prime instead, where B prime is everything that I knew except for the things that were use novel. So for example, in Einstein's case, we leave out the precession of Mercury from B because we happen to know that, or we at least think, that Einstein did not use that information in constructing his theory. Okay? So use novel information is allowed to be left out of the background thing, and now Bayes' rule works again, and we have a response to Gleamore. Okay, there are other responses. It doesn't really matter whether you accept this response. Some other people think it should be part of what you learn. So logical facts that you come to know might be information that maybe Einstein didn't know that the perihelion followed from his theory. So that's some new thing that he learns. Various proposals for how to respond to Gleamore's worry about old evidence. But the main point is, to the extent that Bayesianism has a problem, it's a problem with explaining why old evidence counts at all, not with explaining why double counting is bad. So I think Verndl and Steele got that exactly backwards. Okay, so the B prime here is you're not including your use novel background knowledge. Okay, so this is my main point here. My main point is Pache, what Verndl and Steele said, Bayesianism does not have a direct lesson for us about how good old evidence is versus how new evidence is. That your attitude to that has to be put in by hand into your philosophical framework, right? Bayesianism is mute about whether old evidence is better than new evidence. In fact, if it says anything, it says the relatively implausible thing that old evidence is always completely worthless. And that seems wrong, right? That seems wrong. So it seems like something has to be put in by hand into Bayesianism to accommodate old evidence, and it's not clear what we put in. Okay? So we're left with lots of options, right? And Bayesianism does not tell us which of these options is correct. We're left with the possibility that old evidence is never allowed, right? That seems kind of implausible, right? So in other words, everything should be in my background knowledge. You might think that old evidence is only allowed when it's use novel. So nothing that is not use novel, old knowledge, ever counts as evidence of anything. You might think old evidence is always allowed and it's just as good, right? That seems to be what Verndl and Steele are arguing. That seems also implausible. You might think old evidence is allowed, but it's inferior to new evidence, right? In other words, accommodation gives you some boost in your model, your belief in your model, but it's inferior to prediction. Okay, so there's just lots of options here. There's lots of options here, and the the Bayesian framework itself was kind of mute about that. That's the main point I want to make so far. Okay, so different attitudes you can have to prediction accommodation, and just saying that you're a Bayesian doesn't settle the question of, I gotta put this down because I keep thinking it's gonna move the slides for me. Okay, so let's call predictivism the philosophical view, or the family of views, any view, right, according to which new evidence is at least sometimes somewhat better than old evidence. Right? So if you don't have the view that old evidence and new evidence are always equally good, then you're a predictivist. So everyone that I've quoted other than Verndl and Steele are predictivists. I assume most of you are predictivists of some variety or other. I think when I tell most people that there are these philosophers who have this non-predictivist view, they think that's nuts, right? Surely sometimes using the data that you tuned your model with to evaluate the model is just bad methodology. So we're all predictivists of one stripe or another, I think, right? But there's sort of three questions that you can ask, three different things you can ask about a predictivist. A couple of these I've already mentioned, right? Is old evidence worthless, or is it just weaker? Is old evidence always weaker or always worthless, or just in some circumstances but not others? And then a third question, which I haven't mentioned but I want to talk about, and is the question: is new evidence intrinsically better than old evidence? And that's a very sort of, I think, philosophers that's a very philosophers kind of carving up of things. So it might take me a minute to explain what I mean by it being intrinsically better. So here's one reason to think that it might not be intrinsically better. And this is what some philosophers have called the paradox of predictivism. And the paradox goes like this, right? Intuitively, we tend to think that confirmation, that's the word we use to mean like how you evaluate your hypotheses in the light of evidence, it should just be a relation between theory and model on the one hand and evidence on the other. The psychological or biographical properties of the person who made the model should be irrelevant to how well the evidence supports it, right? And here's a little thought experiment that maybe is meant to prime your intuition for that, right? Imagine that I came to you and I said, I found some secret diaries of Einstein's. I was just telling people on the walkover, we did just find some secret diaries of Einstein's, and they were not very nice. Apparently, he had some disappointing things to say about his travels. But anyway, suppose we found this imaginary diary, and in it we find out that Einstein, when he was constructing the general theory of relativity, did very closely appeal to the perihelion of Mercury data, right? So now we find out that the perihelion of Mercury data is not use novel in the way that we thought it was a minute ago. Are we really going to change our minds about how well we believe in the theory of relativity as a result of discovering this peculiar psychological biographical fact about Einstein? That seems implausible. So the idea that this might suggest then is that while we're all probably predictivists, we all think that prediction is better than accommodation, at least in some cases, at least somewhat better, maybe it's not intrinsically better. Now, what do I mean by that? So it's the idea that it's not. I'm going to skip this slide and go to this one to kind of explain the idea first. And now I'm really going to, I'll try not to walk away from the mic. Okay, so here's what you're meant to imagine. You're meant to imagine, first of all, that you encounter a scientist, and she has collected these 4 bits of data. Okay? And on the basis of collecting those 4 bits of data, she says, here's my hypothesis. And she just connects out those 4 pieces of data with a straight line. And now she says, oh, I just found a 5th piece of data. Do you want to know whether my model successfully predicts that 5th piece of data? You'll probably say, what do people think, right? How much do you care now whether that 5th piece of data is properly predicted by the model? Show of hands, like a lot, a little. Okay. How about in the second case? Now in the second case, scientist has 5 bits. How many? There are 6 bits of data here, right? 6 bits of data here, and now a 7th bit of data is going to come in. Are you as eager to know whether this model fits the 7th piece of data, more eager to know, or less eager to know than in the first case? How many people are more eager to know in the second case? Is that all the hands I can get? I was hoping to get a few more hands than that. Why might somebody be more, tell me why you might be more eager to see the 7th data piece in the, how about in the back? Yeah.
Predicts a lot more structure.
Can you say a little more? I think we're on the same page, but can you?
A lot more structure in the second one, which is not necessarily justified.
There you go, right? There's this, I think that maybe somebody else want to say why somebody else who put their hand up, why do you care more in the second case?
If our model can predict a 7th dot in the second case, then the model's a lot more sophisticated, predicting a lot more nuance.
Yeah, so here's how I would put it. The model on the left kind of wears all its virtues on its sleeves. We can see exactly if that's the right model. It's perfectly obvious why that's the right model. It's a linear model. It's a f equals 3x or something, right? So it just looks prima facie pretty strong that this scientist has gotten the right model. We're going to be already pretty convinced that this is a good fit, right? And I take it you'd be pretty surprised if the 5th data piece came in wrong. Over here, you're going to be really impressed if that 7th data comes in, right? Because it looks like this person just played connect the dots, right? It looks like this person just played connect the dots. Here's one way to think about what's going on then, right? We care a lot about prediction. When there are features of the model that we can't really assess very well for ourselves. There may be hidden features of the model, right? This model here has no hidden features. It's a linear model. You know exactly how good that is. You would know as much about how good that model is by looking at it as anything. But over here, right, this is, I think, what people were kind of getting at. I take it in the audience, right? This model has so much structure, but of course it's completely hidden structure. You don't know anything about why this model like wiggles like that or whatever, right? So now you're really eager to know whether it can predict, because if it does predict, right, you're going to take that, and this is the idea I want to push. If it does predict that correctly, you're going to take that as evidence that whatever that complex structure that was in there, it had features that were good that you were unaware of, right? There were good features in that complex structure that you were unaware of, and the fact that it was able to predict is a sign that had you been aware of those features, you would have endorsed them. So that's the idea. That's the idea of this solution to the paradox of predictivism, which was due to Eric Barnes, right? It's this idea that the ability to make novel prediction is not intrinsically epistemically good. It's a sign of some hidden positive qualities of a theory or a hypothesis or a model. Okay? So the idea is if you kind of have great sort of God's eye view of what's going on in the model and in the science, and you can kind of see every aspect of it, in that situation, you kind of don't really care what's a prediction and what's an accommodation. But it's when there are kind of hidden things where you can't really get under the hood of the model and see what all of its good features might be, right? So, and that I think that's supposed to support the intuition we have in the Einstein case that, look, we know general relativity is like the only way we can come up with of giving a relativistically covariant rewriting of Newton's laws of gravitation. So it's like it's that or nothing. And so when it predicts or accommodates or whatever, we think, okay, whatever, right? Whatever virtues this theory has, we can see them. And so whether it's predicting or accommodating is not really that interesting to us. But I take it when we're evaluating models for skill, these were all, right? These are all just slides that we're going through. Okay, so this is this view that you might call temperate predictivism, right? It's the idea that when prediction is better than accommodation, it's not so intrinsically. It's not part of the real logic of the relation between evidence and theory. It's because when somebody can predict, we take that as a symptom that his or her model has some nice features that we may or may not be able to see for ourselves Okay? In the case of the straight line there, it was like you were like, oh, well, that model is so simple. It's obviously a virtuous model. So the idea then is that prediction is only better than accommodation when, unlike in the example of the straight line, we're unable to assess every possible good-making feature of the theory or model. Okay? So in a sense then, my answer to the question, when is prediction better than accommodation? Prediction is better than accommodation when, and in proportion to, when we're in this sort of epistemically opaque situation of not really being able to get under the hood of the model or theory and see what all its virtues are. We're using it as a kind of proxy for what we think might really be going on, namely the good virtues that the theory model might have. Okay, so right, the temperate predictivist says in the straight line case, look, it was perfectly clear what you were up to here. You were proposing a linear model. I presumably have whatever priors I have on a linear model being correct, and so I just don't really care that much if the fifth point that's going to fit that line gets predicted or accommodated. But in the other case, I had no idea what you were up to, right? And somebody this morning gave me a nice example of what this might be. If I then told you, oh, what's going on here? This is housing prices, right? If I said, oh, this is housing prices, and what's going on is they're kind of gradually going up over time, but they're seasonally varying. Then you might go, oh, yeah, okay, I see now. Yeah, that's a pretty plausible model of housing prices. Now you're not going to be that surprised and not necessarily that much more impressed, right? If I can predict that the next point's going to be there or there or there or whatever, right? So the more you know about what's going on, the more you kind of see inside the model, the less impressed you are by that advantage of prediction over accommodation. That's the claim anyway. Think about whether you think it's plausible or not. Okay. If it is, here's the moral of that story, if it's right, for complex computer simulations. I think at complex computer simulations, particularly ones that are full of parameterizations and approximations, and ones that we're evaluating them for skill, and ones where they're involving a number of balance of approximations, it's particularly difficult, I think, to evaluate whether those kinds of models have the good-making features that prediction is meant to be a sign of. Okay? Simulations have a number of features that are opaque in that regard. And I've got some great examples of that, right? I mean, I was talking to an astrophysicist he works with the fire code, if any of you know what that is. And I said, okay, when I turn up, gosh, I remember the example better. If I turn up the rate at which, neutron stars explode or something like that, I expect this to happen. And then the opposite happens in the model, right? So in these kinds of sort of detailed, complex models like that, where you don't really have a grip on what's going on, I think novel prediction is particularly important, right? And that's, I think, particularly important, right, when you know that your model is succeeding as a result of balance of approximations, because it's very hard to know, right, how robust your balance of approximations is. Does it only work in the data set that you tuned it to? Does it work in other data sets, right? That's kind of epistemically opaque to you, so prediction is especially important to you. Okay, 2 lessons about this, one for climate science, one for cosmology, and then I'll wrap up. How am I doing on time? Let's see.
I think you're okay.
Yeah. Okay, good, perfect. Okay, so 2 lessons, one for climate science, one for cosmology. Climate science, because climate models, right, are those models and their skill are a subject of, I think, right, significant public importance. I think we should recognize the following thing: the epistemic opacity of a climate model is not the same to a climate scientist as it is to us, assuming there are no climate scientists in the room, right? So some of the, if you look at these quotations, right, about how bad is double counting, I think the answer is it depends who you are. If you are the climate scientist who built the model and who knows all of its inner workings and is only uncertain about whether the balance of approximations that she's chosen is brittle or not, then prediction is everything and accommodation is worthless, right? But if you're a lay observer if you're a lay observer and you are the situation is quite opaque to you, right? The ability to accommodate might provide obviously not as much epistemic value to you as prediction, but it might have some value to you because you don't know, right? You don't know the extent to which, for example, the model has accurately captured the physics versus relied on parameterizations, et cetera. So the answer to the question, how much better is prediction than accommodation, not only depends on the situation, but it depends on who you are, I think. And I think in the climate case, because it's such an important politically science, right? There are a variety of lay observers, right, have more stake in whether the models have skill or not, obviously, than many other sciences. And so that's worth remembering, I think. Cosmology. I just want to give one little example of a debate about prediction and accommodation. So as most of you probably know, right, the behavior of galaxies, if we look at galaxies that are observable to us, they spin too fast compared to the amount of mass that they seem to have, right? They look like they should be flying apart, given how fast they're spinning and given the observable amount of mass. And the standard view of what's going on there, of course, is that they're mostly made up of dark matter, right? So there's a lot of matter. That matter is actually holding things together more tightly than the visible matter is, and that's what's balancing out the centripetal acceleration. There's a puzzling fact, right? There's a puzzling fact if you think that's the right account of what's going on, and it goes under the sometimes called the baryonic Tully-Fisher relation. Tully-Fisher relation. It's sometimes called the mass discrepancy acceleration relation. And what it is, this is Stacy McGaugh, who's a proponent of abandoning dark matter and instead replacing the laws of physics to accommodate this. He's very fond of pointing out that there's a very, very nice simple curve that you can use to predict the rotation of a galaxy just from its observable mass. Now that's puzzling, right? That's puzzling if you think that 4/5 of what's determining the gravitational attraction in there is the unseen matter, right? It's puzzling. This was a tweet that I think he tweeted this. Yeah, he tweeted this at me a couple of weeks ago. I think one prime philosophical issue is that of a prediction versus accommodation. I can accommodate pretty much anything with invisible mass, right? Give me any rotation curve you like. Just put enough mass on there to make it balance out and you're good. What I can't do is use it to predict a priori the things that his theory, modified Newtonian dynamics, Mond, gets right a priori. But I can always come up with some story after the fact. So he's very keen as a defender of modifying the physics as opposed to allowing the existence of dark matter. He's very keen of pointing out that he can predict this. And a couple of other astrophysicists asked me once, and I said, you know, Eric, Stacy keeps saying that like every time he finds a new galaxy, that's a new prediction, and that's like a new piece of data against us. Is that fair? Is it fair to think like every new prediction of a new galaxy, that's new evidence for Mond? Okay, so I think my story here actually has a nice answer to that, right? And the answer is, it's true. It's certainly true that it's a virtue of Mond over the dark matter theory. Lambda cold dark matter is kind of the name of the full name of the theory, right? That it can predict rotation curves without much greater ease. But how should we understand this, right? I think we should understand this in the following way, right? That this curve is there's a nice simple power law here. And the people that propose Mond have a nice simple explanation of that power law, right? Their explanation is that's built into the force law. That's exactly what instead of the force is proportional to r squared, it's some other formula, and it's just read right off of that curve. And I think there's nothing, prediction, accommodation, whatever, it's sort of irrelevant at this point. This model wears all of its properties on its sleeves. Whatever your prior in this being right is what it is, and you should no longer be particularly excited about new predictions, right? It is what it is. That's a feature of the universe that has this curve. Now, there are, of course, now two possibilities. This curve exists because that's the law of physics, or because it's some really complicated emergent process, right, of how dark matter emerges out of the cosmic, out of the structure that we learn about from the cosmic microwave background. That's all about how the dark matter clumps. Once it clumps in the way it does, the visible matter, interacts with it, and somehow out of all of this emerges this law. Okay, and right. So in land of cold dark matter, that Baryonic-Teller-Fisher relation is going to be a very highly emergent phenomenon, and it's going to be hard to understand why we get that. Now, there have been a few papers, and Stacy, the monitor, is quite critical of these. And the papers say, this is a nice title, it says, the mass discrepancy acceleration is a natural outcome of galaxy formation. Right? So what have they done? They do these big simulations of the kind I showed you at the beginning of the talk, where all the dark matter is like distributed according to the cosmic microwave background, then it clumps together, and then once it gets down to about, I think, 10 megaparsecs, that's when the baryonic physics kicks in and all the feedbacks happen, and boom, out pops the Baryonic-Teller-Fisher relation. And now you want to know, okay, have you actually explained why we observe the Baryonic-Teller-Fisher relation under land of cold matter? Now I really want, in this case, I really want to know, right? I really want to know what parameters did you tune? What data was accommodated here? What data was predicted? And now I need to answer a really hard question, and I don't know how you answer this question. And it's the question that I think was really nicely captured in Gavin Schmidt's quotation, namely that if it's an irreducible fact about these kinds of simulations that they're going to be tuned, to data sets, how do you decide if the features that are in the data set used to tune are sufficiently different from the ones that you think you're skillfully predicting to be able to convince your audience or whatever that you have not double counted, right? How much covariance is there allowed to be between your data set and the one that you tuned with and the one that you're using as your evidence? And I think, if you want to know, right? If you were involved in this debate and you wanted to know how many points does this count in favor of Mond and how many points does it count against lambda cold dark matter, presumably when this paper comes out, that score might change a little bit, right, in your epistemic assessment of that situation. But in order to decide how much it changes, I think it's a really, really hard question to know how different, like how much tuning did they do? What data sets did they tune to? How different are those data sets? How much, in other words, how much of that Baryonic-Teller-Fisher relation might have been in the data set that they were tuning to? If it was already in the data set that they were tuning to, then thumbs down. If it wasn't, maybe thumbs up. But I think that's kind of, in a way, one of the most difficult questions of computer model assessment is how different are my test data set from my tuning data set. Thanks. I think that's, yeah, thanks.
I got absorbed and lost all track of time, but we do have a little time for some questions.
That last bit is really compelling. I like it because it brings in soap opera aspects of scientists arguing.
Yeah.
But it also seems to me like you're playing to a common trick or trap that we all fall into. We have some empirical data, and then we fit something to it, and we say our model is true. But the model itself is not true. The point of the model is to figure out if you've come up with a set of logic that is consistent with whatever data you can possibly test it with, right? So you have here Mond on the one hand. The question is, I don't know enough about it. If it was developed independently of this then this is and it fits well, and we've shown that that logic seems to be consistent with some way that the universe works. And equally, the dark matter folks can show that if with some tuning, perhaps,
Yeah.
you can come up with something that's consistent with the data. Is that the tuning isn't right or wrong or make the model worse or better? It leads to the next question of whether.
I think I want to press my point a little bit, because I think my point cuts a little bit against what you said. My view is that insofar as you think that this just is the law, I kind of don't care. I kind of don't care whether you predicted or accommodated, because I think this model, right, kind of wears all of its epistemic credentials on its sleeve. It's a power law, right? It's simple. You either like that or you don't. And I don't really care, and I don't actually know which of these data points was collected before I take it some of them were there first. Nobody would have guessed Mond a priori. You had to have some of these data points. So some of them came before and some of them came later. And my view is, in a nice, simple model like this, I don't care that much about what was predicted and what was accommodated. In the other case, right, where these guys put everything in the kitchen sink into the model, dark matter and 7 kinds of feedback and 14 parameterizations, and they tuned it some, and then poof, out came agreement with this data. Now I'd rather see. Now I'm really much more interested in, did you accommodate? Did you predict? If you were predicting rather than accommodating, how different was your data set? So I think in a way, my point was that there's a really big spectrum there, and it's about that complexity of the model. Yeah.
The one reason general relativity, is as good as it is that you can accommodate. You could have known all these things ahead of time, but you have a really heterogeneous set of pieces of evidence, all of which are nicely accommodated, right? I mean,
With if you allow yourself to sprinkle dark matter everywhere you want. Otherwise, it's terrible at getting the acceleration curves. Yeah.
I guess, but ultimately, the value of models like these, if you're trying to explain how things work, is whether they work for many different situations. I'm not trying to predict the stock market.
Yeah, right.
And finding another galaxy that fits the same curve, like you said, is not that surprising for either model once you've accommodated enough data.
Okay. Yeah. Sorry. Maybe we should. You wanna?
So I saw Frederick.
I go to a little bit lower layer than your talk is about. So most of the scientists, a great number of scientists, are driven by curiosity, and reward is understanding.
Yeah.
I haven't used word understanding many times, 3 times. In the
So
talk.
yeah.
Is it a part of prediction? But a conventional meaning of prediction is temporal character. But maybe you mean more epistemic character of prediction.
So in a way, right, part of the role of the word skill in the talk is to signal, in particular, that I'm talking about models that aren't very curiosity satisfying. So if I show you, it depends what you mean by curiosity, of course. But if I show you a climate model, if I show you a climate model, and many climate scientists lament this state of affairs. This is a very common thing you hear climate scientists say. They'll say, it's great that we've all been working on this IPCC business for 30 years. This was an incredibly politically important project, but it's corrupted our science. We've been building these incredibly large models with everything in the kitchen sink thrown into them. We've been working exclusively on building models with the best possible degree of skill, right? That they're the best. They produce the best possible predictions, but they don't. They're not. We're not doing what we went into science to do. We're not really learning what are the really underlying processes in the climate, and we need to get back to that. We've kind of done everything we can do, for the public. You people now either need to heed our warning or not, but we really need to get back to trying to So in a way, part of what I'm talking about here are models where, now, of course, you might be curious, and it provides understanding to know is there cold dark matter or is there modified dynamics, but what I think you don't get understanding from for example, right? If you look at this paper, where they get the baryonic Tully-Fisher relation to come out, I don't think anybody would claim that that anybody understands, right? If you're a dark matter proponent, and you even if you believe these simulations, I don't think anybody would say they provide any deep understanding of where the mass discrepancy acceleration curve comes from. It just pops out like kind of magic, if that makes any sense.
Okay.
So I saw a couple hands, and we've got to move on to Jeff.
Is my question or comment is just about the relating the Bayesian analysis you had in the first part of the talk to some of the points you're making in the second part of the talk. So it has to do with the background information.
Yeah.
So I understood very well how if you had a layperson versus an expert, they would have different kinds of background information. That would make a different, different conclusion. In the case of the opaque model, so one that you don't understand very well, does that correspond in the Bayesian analysis to having less background?
No. So what it corresponds to, right? If we go back to that slide, the idea was that once we recognize that there's this problem of old knowledge, right? Once we recognize there's this problem of old knowledge, we have to modify the background knowledge, right? Because if we include everything in the background knowledge, then Bayes is going to say accommodation always is completely worthless.
Right.
And that seems wrong.
Right.
So Bayes doesn't answer the question, right? That's why Gleamar was, why I'm not a Bayesian, right? Bayes does not answer the question, when does accommodation help? And in order to decide that, you need to decide what are you going to leave out of B and put into B prime. So remember in the Einstein case, we said we're going to leave out of B, even though Einstein knew about the Pelihan Mercury, we're going to leave it out because it's use novel. So now the epistemic opacity, right, is about what things are you going to count as use novel and how much are you going to penalize them. So if you're Gavin Schmidt and I'm just, I just walked into your lab and I don't know really that much about climate models, and you say, oh look at these, I got tropical cyclones to form in the Gulf of Mexico or off Cape Verde, whatever, every between June and September. And now I say, okay, well, did you know that? Did you know about that before you built the model? And now I need to decide, if you did know about it, am I going to pull it out of B or not? And the answer might be, well, Gavin has to pull it out, but I might leave it in there because I'm more ignorant, something that was not use novel, I might still think counts as evidentiary.
And so that's why at the end of the talk, when you're talking about that relation, the power law
Yeah.
relation, you really want to know to what extent those, the paper that you referenced at the end, they use that to tune their
Correct.
model.
Or whether, or maybe just as bad, something that was so covariant with it.
Is it novel use or not?
Exactly. So in the opaque case, I really care whether things were use novel, or even if they were sort of superficially not use novel, were they really covariant with something that wasn't use novel? Yeah.
Thanks.
Okay, we're out of time. I saw one hand. You want to go real quick? Or?
I was just going to offer my opinion as a newly minted climate scientist.
Oh, okay. Yeah.
But yeah, it's a lot of black box and relatively little fundamental understanding about the processes driving it. And unfortunately, it is the case where we are trying to predict the future of the stock market. Like exactly. We don't have anything to hold it up against.
Yeah, or we're at least trying to predict like patterns in the future of the stock market, if not the actual exact value or something. Yeah.
It's kind of,
Yeah.
epistemologically maddening.
Okay, well, I think on the last schedule I saw you have the next half hour free. You
Okay.
don't want to decompress, but
I'm also happy to chat with people. So.
continue the conversation. And then the thing I haven't had a chance to talk to you about is if you're up for dinner or not. So I will answer that question, and if you are interested in dinner, tell Lynn to tell me or something like that. I'm Alan Poller, and we'll see if we can twist your arm. Or
Okay.
not,
Is
that's fine.
there already a dinner associated with the other?
There's a group from Livermore and there's a reception. But if you want to do even more eating, we can go to dinner.
Okay.
I figured we would figure
My
that one
my
out.
uncle and cousin and aunt live here, and I think maybe they kind of want me
Okay,
for
no,
dinner
that's fine.
too. Or
So
something.
then-
Okay. So
then-
yeah.
then Eric has plans for dinner.
Okay.
That was what I was fishing for. But you will be at the reception. And
Yes.
yes. Okay.
And that's in like half an hour.
I think it
Or-
was half an hour a slot and then that.
yeah,
So
okay,
we got
perfect.
a little time to chat.